Shutaru. In this example video, usually I'm doing a full lesson, but in this one we're just going to do an example of a related rate problem in calculus. And it's going to be involving putting some water, we'll say, into a cone. So a conical tank is 10 feet across, of course it could be any fluid, but is 10 feet across and 20 feet deep. If water is flowing into this tank at the rate of 8 cubic feet per minute, find the volume, or excuse me, find the rate of change on the depth of the water when the water is reached a fixed depth of 10 feet. Now, it's not going to be fixed depth, of course. You're going to be putting water into this tank and it's going to be constantly changing. But that instant where the depth is 10 feet, how fast will the water be rising? And we need calculus to figure this out because, well, the cone has basically a diameter of 0 at the bottom, increasing to a diameter of 10. So as that diameter increases, the cone is going to be able to hold more volume at some particular value of depth that you're at. So the higher up this cone you're going to get, if you're pouring the water in at a fixed rate and not changing the rate at which the water is going into the cone, the rate at which it's rising is going to slow down. It's going to be variable. Okay. So if we're going to do a related rates problem, we need to sort of, figure out all the variables that we're given and what variables do we care about? What variables are we going to be trying to figure out at the end of the problem? Well, it says find the rate of change of the depth of the water when it's 10 feet. So we're going to be looking for a rate of change. That means derivative. So we're going to be looking for dH dt. What's the rate of change for the height at some particular point in time? That's going to be set by the fact the water's 10 feet deep. Okay, well that's what we don't know. Well, what else are we given? Well, we're saying that we're putting water into the tank at 8 cubic feet per minute. Well, that's volume. So the rate of change for volume, dV dt, is going to be, in the unit of time measure is of course per minute, is 8 cubic feet per minute. So 8 cubic feet per minute, kind of getting a little bit messy there. And seems like that's what we have. We've got the overall depth of the cone. We have, now I've marked off the fact that the radius is equal to 5 because our volume formula for a cone doesn't use diameter, it uses the radius. So if the overall diameter is 10, then the radius is 5. And thus we're also going to mark off this depth of 10 feet for the water and some radius, which we don't know at this point, for that depth of 10. Okay, now what do we do next? Well, maybe you know, but we can also just let the math tell us what we need to do next. We're talking about rates of change, so we're talking about derivatives. So we have volume, or V, is equal to 1/3 pi r squared h. So we're thinking, okay, derivative, so dV dt, because we're going to be finding the derivative with respect to time, is, so you can't just write V prime, it's kind of confusing that way, is equal to, now my equation here has two variables in it, and both of these variables are going to be variable. The radius at which you have the water is going to be changing as the water increases in depth, and of course the height is going to be changing. So to find the derivative of this function, we need to use the product rule. So it's going to be the first factor times the derivative of the second factor plus the second factor times the derivative of the first, which means we're going to need to use the chain rule. We're going to take that 2 and multiply it by 1/3. Reduce that power by 1, which is just going to be r. And then again, because we're finding the derivative with respect to time, it's not just that, you have to multiply by the derivative of the base, so I don't know why I put that parentheses there. Okay. Now look at our derivative that we have for volume. I could clean it up a little bit, but I don't need to worry about doing that because I see that, well, in my derivative it's asking for the rate of change for the radius. And I'm not given any information about that, and that means I'm just going to really overcomplicate the problem if I try and work with this formula initially, both in terms of R and H, because all I care about is finding out how fast the water is rising, the change in the depth, or I have labeled as H for height. So let's rewrite this formula so we don't have a variable of R in it and don't have to worry about that rate, which we're not given. So excuse the interruption, my dog started barking, so I wanted to wait for them to stop, calm them down. Okay, so we're looking for this, to get this equation in terms of just h. Well, the sides of the cone is going to allow us to do that. The cone with the straight sides has given us a constant slope, showing us a relationship between the radius and the height. So let's see here. We have, what is the ratio of the rate of the height of the cone, or then the water was going to be, the height is going to be over the radius, or you can do r over h. Doesn't make any difference when you set up equal ratios as long as you're consistent with both of those fractions or ratios. So the overall height of the cone is 20, and the radius of the cone is 5. And this relationship is constant again because it's a cone. The sides are linear functions or lines, so the slope is going to be constant, and that's going to allow us to write that equation in terms of only h if I solve this for r. So if we cross multiply, we have 5h is equal to 20r. Divide both sides by 20. Trying to solve for r so I can take the r out and plug in some kind of expression that just has an h in it. And so we have r is equal to 5 over 20 is 1/4. Excellent. Well, now I can come over here and say, well, now my volume is equal to 1/3 pi times r, which is going to be equal to 1/4 the height, squared, times h. So now I have volume in terms of just h. Let's just clean this up a little bit. We have volume is equal to 1/3 pi. 1/4 squared is 1/16. And then we have h squared times h. Cleaning this up a little bit more, we have volume is equal to 3 times 16 is going to be 48. So 1 over 48 pi. Now let's put that pi on top. H squared. Excuse me. When you multiply like bases, you add those exponents. So h squared times h to the first is going to be h cubed. Now, when I find the derivative, I'm only going to have a value for, or a variable of the volume or the rate of change. So dv dt, the derivative with a volume in respect to time, or the change of volume over the respective time. 3 times pi over 48 is going to be 3 pi over 48 times h squared. And again, we're finding the derivative with respect to time, not just with respect to h. So we got to multiply by the derivative of that inside function, or that base, which is going to be dh dt. And that simplifies to be 1 over 16. So let's just do that. Okay, now that I've taken my volume, I've found the derivative, basically implicitly if you will, or not basically, I did, and I have the change in volume is equal to pi over 16 times the height squared times the dh dt, basically the rate of change for the height. And now I can finally bring in that fixed depth of the water being 10 feet. Now that I've found the derivative, and that allows us to have some variables in here about rates of change, I can go ahead and plug all these numbers in. The water is flowing in at 8 cubic feet per minute, so that's 8 is equal to pi over 16. Their fixed height, we want to find the rate of change of the depth when the water is 10 feet deep. And we're looking for dh dt, and I'm starting to run out of room, and I'm getting to a point where I need to, worry about making sure I don't make any small calculation errors in my head. So of course, well, I can do, obviously 100 squared is 100, 10 squared is 100, so we get 8 is equal to 100 pi over 16 dh dt. And if we wanted to make sure we kept this in exact format, we would take this, and we're going to, right off the top of my head, multiply both sides by the reciprocal. So dh dt is equal to 8 over 1 times, take this fraction and flip it, multiply it to both sides of the equation, so times 16. I could have this reduced, but And if you're looking for, again, an answer in exact format, this is going to be dH, dt, 80 and 48 is going to be 128 over 100 pi feet per minute. And of course that 128 over 100 is reduced, but I'm pretty sure, yeah, I have my answer both in using your notes are only good if they don't have any mistakes in them. I had 2 decimal approximations for the rate of change. Realized one of them had to be wrong, and apparently I should have erased one of them. The 128 over 100 pi reduces to 32 over 25 pi feet per minute, and that's again the rate of change for the depth of the water when it is 10 feet deep. And the decimal approximation of the answer to 3 decimal places is 0.407 feet per minute. I'm Mr. True. Go do your homework.